Okay, in today's lesson, we're going to learn something called the integral test, and we're going to also learn about p-series. So the integral test says if f is positive, continuous, and decreasing. So those are the three conditions that must be met before you can apply the integral test. For all x greater than or equal to 1 and a sub n is equal to f of n, we could say that if the integral, the integral from 1 to infinity of f of x dx converges, therefore the summation of n equals 1 to infinity of a sub n also converges. Likewise, if the infinite integral diverges, the series diverges as well. So integral converges, series converges. Integral diverges, series diverges. So how you do this, first you'll let f of x equal that natural log of x over x. We're going to determine if our conditions are met. So remember, our conditions are f of x must be positive. So just looking at, you can look at different terms in your head. You can do this. Just kind of state on there if it is positive. So this is positive. And then because we know that f of x cannot equal 0, x cannot be 0, we start with x equals 1. And we know the natural log is always a positive value, and then x is always going to be a positive value. Positive divided by positive gives us a positive value. So that's how we know this, okay? Then you have to check and see if natural log of x over x is continuous. And it is for continuous. The only time that that does not work is for values where x equals 0 or negative, but our domain is where x starts at 1 and goes up. So therefore, since we know x is greater than or equal to 1, it's continuous. And the last thing you have to check for is this function decreasing? Now, the easiest way usually to check decreasing is just to find the derivative, because if you know if the derivative is negative, your function decreases. So to figure out if f of x, which is the natural log of x over x decreases, we're just going to differentiate this. Quotient rule, so that's low d high minus high d low over low squared. Okay, simplifying that down, I end up with 1 minus the natural log of x over x squared. Now, x squared will always be positive because you're squaring that value. The natural log of x will give us values that are greater than 1. So if I take 1 minus something greater than 1, I'm going to get a negative value. And so I have negative over a positive, which is negative. So therefore, I can conclude that f prime of x is less than 0 when the natural log of x is greater than 1. And where does that happen? Well, where does the natural log of x equal 1? That's when natural log of e is equal to 1. And so that would happen when x is greater than e. And so remember, it doesn't matter if it's happened at the first few terms. It's what happens later on toward infinity that we're dealing with here. So it meets all three requirements. So that means all I need to do, now that I know, in order to find the summation of this, all I need to do is evaluate the integral. So I'll go up here. The integral of 1 over infinity of natural log of x over x dx. Okay, so remember infinite integrals, we rewrite that as the limit as b goes to infinity of the integral from 1 to b of the natural log of x over x dx. I'm going to solve this using u sub. I'm going to let u equal my natural log of x. Du therefore has to be 1 over x dx, and dx would then be equal to x times du. And so my x's cancel out, and I'm left with the limit as b goes to infinity of 1 over b times u du, which is easy to integrate. So the derivative of u is u squared over 2. And remember, my u is the natural log of x. So I have the limit as b goes to infinity of the natural log, well, u squared over 2. I guess I'll write that. Of the natural log of x, quantity squared, divided by 2. Evaluate it from 1 to b. And so that's going to give me the natural log of b, quantity squared over 2, minus the natural log of 1, quantity squared over 2. The natural log of 1, quantity squared over 2. Well, natural log of 1 is 0, so that's 0 over 2, which is just 0. And so that's going to give me the limit as b goes to infinity of the natural log of b, quantity squared, over 2 minus 0. And then let's see what's happening. The natural log of b, that's going to infinity. Infinity squared is infinity, divided by 2 is still infinity. So infinity minus 0 is infinity. So this series diverges because the limit diverges, goes to infinity. And so you need to write your conclusion. So the series, natural log of n over n diverges, and then how you figured out diverges. We used the integral test, so by the integral test. Because we're going to learn a lot more tests in this unit. So you always have to identify the test you use to determine the divergence or convergence of the series. All right, looking at this next example, let's determine if this converges or diverges. So first check and see if your 3 conditions are met. So this is a rational function. It's always continuous because x can equal any number. It is always positive. Denominator is always going to be positive. 1 is always positive. And let's find our derivative here to see if it's decreasing. Okay, I'm going to start by rewriting our derivative so that I'm going to move that x squared plus 1 to the first. So I don't have to use the quotient rule. I can just use the product rule. And then don't forget to multiply by the derivative of the inside using your chain rule. Rewriting this, I now have my derivative is equal to negative 2x divided by x squared plus 1. That numerator is negative. The denominator is always positive. And so that gives us that this derivative is negative. And so it's less than 0. And we can apply our integral test. So now I just need to find my integral from 1 to infinity of 1 over x squared plus 1 dx. So that's the limit as b goes to infinity of the integral from 1 to b of 1 over x squared minus 1. Hopefully by now you're recognizing that as our inverse tangent function. So that's the limit as b goes to infinity of our arctangent of x, evaluated from 1 to b, which is the limit as b goes to infinity of arctangent of b minus arctangent of 1. Well, what is the angle whose tangent is infinity? If I plug in infinity in place of b, well, looking at our graph, the angle whose tangent is infinity would be pi over 2. And the angle whose tangent is 1 is pi over 4. Pi over 2 minus pi over 4 is pi over 4. So that gives us a value. So therefore, we know our series converges to pi over 4 by the integral test. All right, let's determine if the function 1 over x, natural log of x, is positive, continuous, and decreasing. So let's check and see. X cannot equal 0. X could not equal 1. But notice our series starts at n equals 2. So yes, a positive works. Continuous, yes, it's continuous for any x value greater than or equal to 2. And decreasing, well, let's find our derivative to determine if this is decreasing or not. So derivative of the outside times by the derivative of the inside. That's going to give us 1 plus natural log of x divided by x squared, natural log of x quantity squared, times by negative 1. And so that's a positive on top, a positive on bottom, times by the negative 1 on the outside, which gives us a negative value. So yes, this function is decreasing. So that means I can apply the integral test by finding the integral from 1 to infinity of 1 over x natural log of x, or the limit as b goes to infinity of the integral from 1 to b of 1 over x natural log of x. I'm going to do u sub for this. I'm going to let u equal my natural log of x. And therefore du would be 1 over x dx, and dx would there be equal to x du, and so our x's can cancel out. That leaves me with 1 over u du. And the integral of 1 over u is the natural log of u, so I have the limit as b goes to infinity of the natural log of u, and the natural log, and u we know is the natural log of x. So I can rewrite this as the limit as b goes to infinity of the natural log of x, all evaluated from 1 to b, which would give us the limit as b goes to infinity of the natural log of b, minus the natural log of the natural log of 1. So we know the natural log of 1 is 0. So the second term is 0, but we know the natural log of b is infinity, and the natural log of infinity is infinity. And so we know this has to diverge to infinity. So our conclusion would be this series diverges by the integral test. Okay, we've already learned about harmonic series and geometric series. Now we're going to learn a new series called a p-series. P-series is a series in the form of the summation of n equals 1 to infinity of 1 over n to the p, where p is any positive constant. So that would go to 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, etc. You might notice that with p equals 1, that is a series that we've already talked about a little bit, and that was the harmonic series. And then recall that the harmonic series diverges. So the key with a p-series is can be any positive constant, and the harmonic series is a special case of the p-series where p is equal to 1, and that p-series diverges. So our first theorem we need to learn is called the convergence of the p-series theorem. That simply states a p-series, again, that's 1 over n to the p, summation of 1 over n to the p, converges if your p-value is greater than 1. So converges if p is greater than 1. It diverges if your p-value p-value is from 0 to 1, including the 1, because remember, harmonic series is diverges, so we include the 1 for the divergence. So all you have to do in order to figure out if the p-series converges or diverges is first you tell me it's a p-series, and you identify what your p-value is, in this case 9. 9 is greater than 1, so our conclusion, it converges. Okay, try B. First off, you want to rewrite this as a p-series. So I'm going to replace that fifth root of n as 1 over 1 to the n to the 1/5 power. And so this is a p-series with p equal to 1/5. 1/5 is between 0 and 1. So therefore it diverges. The C-series, the second one might not look like a p-series to start with, but you factor out that constant 5, and you have the summation of n equals 1 to infinity of 1 over n, which is a p-series where p is equal to 1, or you can just say this is a harmonic series, therefore it must diverge. Now we're ready for our next test for convergence. It's called the nth term test for divergence. So this one will only tell us if the series diverges. It will not tell us if it converges or not. It just tells us if it diverges. And basically, this theorem simply states, this test simply says, if I find the limit as n goes to infinity of a sub n and I get anything except 0, I know the series converges. The problem is if I get 0, this test fails and I must figure it out another way. Okay, so make note of that. The nth term test only tells us if it diverges. Okay, so let's look at this one. We have the summation of n equals 0 to infinity of 2 to the n. We want to figure out if it converges or diverges. So I'm going to figure out the limit as n goes to infinity of 2 to the n, and I get infinity. Okay, infinity is not 0. Therefore, I could say this series diverges by the nth term test for divergence. Remember to identify which test you use in your answer. Okay, so the summation of n equals 0 to infinity of n factorial over 2n factorial plus 1. All right, so let's try finding the limit of this series. Okay, so we have the limit as n goes to infinity of n factorial over 2n factorial plus 1. Now, because of the end behavior model, that plus 1 really means nothing as n goes to infinity. That factorial is going to go up so much faster. So I can just simplify this down to simply 1/2. And so the limit as n goes to infinity of 1/2 is 1/2. And so my conclusion is that this series, the nth series, diverges by the nth term test. Since the limit as n goes to infinity of a sub n is not equal to 0, I can conclude that the series diverges by the nth term test. Okay, looking at number 7, now we have the summation of n equals 1 to infinity and 1 over n. We're going to determine if this converges or diverges. Okay, so if I want to do the limit as n goes to infinity of 1 over n, that would give us 0. And since the nth term test says it cannot equal 0, but this equals 0, the nth term test fails, for divergence fails here. So we cannot use that to determine if this series converges or diverges. Okay, because the theorem only says it cannot equal 0, it diverges. If it equals 0, it does not tell us anything. So we cannot, the nth test does not apply. So we must choose another technique to figure out if this series converges or diverges. Well, if I look at the summation of n equals 1 to infinity of 1 over n, I realize that this is a p-series where n is equal to 1, or I could recognize this as a harmonic series, and we know harmonic series diverges. So my conclusion, it diverges because it's a harmonic series.